Okay, so in this video, we're going to look at rotational dynamics. So again, we're still making that comparison between linear quantities and angular quantities. So which the first thing I want you to remember is look about way back in Unit 2, um, that forces cause changes in, sorry, let me pull up my pens. Right, so forces again cause changes in motion, right? Without a force, you can't accelerate an object. That's because that's what they want to do. They want to accelerate objects. And then Newton's second law, right? Remember, tells us that when an external force is exerted on an object, the object acceleration is given by the equation F equals ma. Right? Remember, this was a net force, right? So the sum of the forces equal to mass times acceleration. Now, you have to remember in this unit, our rotational equivalent for force is torque. So torques are going to cause changes in rotation motion, therefore causing an angular acceleration. Right. So again, that rotational equivalent of force is torque, and that causes an angular acceleration. So the way we think about this is that Newton's second law of rotational motion tells us that when an external torque is exerted on an object, the object will rotationally accelerate. Okay, and so what we say is the sum of the torques is equal to I times alpha. And remember, I is what we learned about in the last video, which is the moment of inertia. Alpha, again, is angular acceleration. Now, the thing about it is that there's no difference in the problem solving strategy. So the problem solving strategy for force was draw, sum, solve. It's the same thing here. Okay, so draw the free body diagram, right? So that's the first step, is to draw that free body diagram. Next thing we're gonna do is we're gonna sum, right? So what we're gonna have to do now is you have to sum the forces and the torques. Okay, so you have to sum both of those. And then finally, you're going to solve for what you're looking for, right? It could be a tension, it could be the angular acceleration, it could be a linear acceleration. And also remember that the linear acceleration is r alpha. So you may have to use this at some point in time, right, to help you solve for any accelerations. Now, what's going to happen, like I mentioned before, the free body diagrams are going to look a little bit different because when we drew them linearly, they originated from the center of mass. But for rotational free body diagrams, you're going to have to draw the forces um, at the point of application. So you're going to run into like rolling objects, or you can see kind of peeking down here an Atwood machine, right? So previous questions, the Atwood machine, the motion, or excuse me, the pulley didn't matter. Now the pulley is going to matter. So when I draw a free body diagram of an Atwood machine and a pulley, really the only force that would originate from the pulley, or excuse me, that originate, yeah. So if I'm doing a free body diagram for the pulley, the only force that originates from the center of mass or center of gravity is the weight. Where now the tensions, okay, are going to be hanging out here on the sides, right? Because these are what's causing the rotation. Um, and so you got an R times F factor there, right? So one's going to cause a counterclockwise torque, the other is going to cause a clockwise torque. And so those are the torques that you would set equal to each other and try to solve for if it's moving at a constant speed or so forth. Okay. Now let's look at this question. So this is talking about two blocks of mass M and M1 and M2 are connected by a massless string that passes over a wheel of mass M as shown. So the hint is anytime they give you the mass of the pulley or the wheel, you're going to have to use rotational dynamics. The string does not slip. on the wheel and exerts forces T1 and T2 on the blocks. This not slipping is important. That just means it behaves like a true pulley. When the wheel is released from rest in the position shown, it undergoes an angular acceleration and rotates clockwise, right? So that's what this arrow here is telling us. Um, which of the following statements is true? All right. So the first thing says T1 and T2. T1 equals T2 because the wheel has mass. That really has nothing really to do with causing the rotational motion. In fact, if T1 and T2 are equal, there would be no motion. Okay. T1 and T2 equal because both blocks have the same acceleration, right? If they're both going to have the same acceleration, you know there's going to be a difference because there is an angular acceleration happening. T1 is greater than T2 because M1 is further from the wheel than M2. That's just how the picture is drawn. Okay. T1 and T2 because T1 is greater than T2 because M1 accelerates upward. Um, so what we're looking for is what is the best answer. So yeah, I mean, in general, if M2 is greater than M1, it would accelerate upward. But you know, that's not the exact reason why, right? So T1, T2 is greater than T1 because an unbalanced clockwise torque is needed to accelerate the wheel clockwise, right? So that is our correct answer. And so for this pulley to rotate, T2 must be greater than T1, right? So for this, so this motion has to go down and that's going to go up, okay? In fact, the reason why D is not wrong, if T1 was greater than T2 in this case, the acceleration would be the other way, okay? And so um, T2 has to be greater than T1 because of that counterclockwise torque. Or yeah, so torque slash, angular acceleration. All right. If it was again, if T1 was greater than T2, then it would accelerate the opposite direction. Um, so the next video we're going to look at just revisit our good old friend conservation of energy. Now we're going to bring in this rotational piece to it.